Dubai World Robotics Congress 2020. Mission statements. So we want to be able to support the physical disabilities globally with technology, and in doing so restoring a sense of empowerment and independence for that person. The presentation will begin with an overview of a brain-computer interface showing the components involved. We will take a look at the aims and objectives, and then in section 3 we'll look at the background, and in section 4 the methodology, in section 5 the preliminary results, then in section 6 we'll take a look at the future work, what are the possibilities, and then in section 7 we'll end with the conclusions. In the event of a serious accident or illness, an able-bodied person may lose their left or right hand. The person would lose the ability to grasp objects independently and suffer a loss of independence. There are different ways a disabled person may regain their independence by controlling a robotic prosthetic hand. The person may signal commands to the prosthetic hand in many ways, for example, using electromyogram, obtaining a signal from the muscle activity. In addition, another method could be motor imagery. The person imagines opening or closing their hand. Both scenarios require an intermediate device to interpret the signals called a brain-computer interface, BCI. The following diagram is an overview of a brain-computer BCI system comprising of generic components, EEG data acquisition, brain signals from the user, pre-processing, feature extraction, classifier, robotic prosthetic hand. Using a trained BCI, the disabled person may imagine opening or closing their hand. EEG can be used to detect changes in the primary motor cortex of the brain associated with movement. Sensory motor rhythms detected by EEG over the motor cortex of imagined movements. Before the person imagines movement, there is a decrease in mu, which is 7.5 to 12.5 Hz, and beta, which is 12 to 30 Hz. This is known as event-related desynchronization, or ERD. A relaxation occurs afterwards, known as event-related synchronization, or ERS. A BCI device can be used to detect and classify ERD and ERS, and hence determine a person's intentions. Filter banks and common spatial patterns techniques can be used to enable the classification process by increasing the discrimination between the classifications. The training data is used to train a classifier to recognize when the person is imagining physical limb movement. The following is not connected to a BCI but serves as a demonstration of a potential future development connecting a trained BCI to a robotic prosthetic hand. The person imagines closing their hand, signals detected by EEG, or the person moves, EMG detects a muscle signal, and the system interprets that intention, and the robotic prosthetic hand closes. Furthermore, the person imagines opening their hand, signals detected by EEG, or the person moves, EMG detects a muscle signal, and the system interprets that intention, and the robotic prosthetic hand opens. One of the objectives would be to interface the robotic prosthetic hand to a brain-computer interface. There are other methods of actuation, such as electromyogram, or a combination of both, and other interface methods. It would be a more natural operation if the interface were operated seamlessly with the person. The person seeing an object and manipulates the object as naturally as if it were their own hands. From the motor imagery, EEG recording and feature extraction, it is possible to develop a classifier to determine the movement intentions of the person. For example, are they opening their right hand or are they closing their right hand? The Adaptive Decision Surface ADS classifier was developed to enhance the performance in classification and determining the person's intentions, such as opening or closing their hand. The light detection and ranging LiDAR system can be used to determine the distance to the object and support object manipulation. Electromyograph could be used to support the classification process. The decision system controls the command to actuate the robotic prosthetic hand. The ADS classifier will be more powerful if it has the ability to adapt. Adaptation is advantageous because the environment and the person both change as time passes. Therefore, having the ability to accommodate changes in the environment or person will increase the reliability and the accuracy of the brain-computer interface. The future objective could be to develop the BCI interface to a robotic prosthetic hand, in addition to electromyography, to have a multimodal input control. The functionality of the robotic prosthetic hand must be seamless and certain to follow the user's intention. Initiation of the movement begins in the motor cortex of the user's brain. Therefore, the intentional movement will be detected first by the brain-computer interface. The object can be manipulated by the user's control, such as grasping an object. The robotic prosthetic hand control system may use proximity sensors, such as LiDAR, along with other sensors, optical camera using infrared. An optical palm camera could be used to recognize objects. The system will be empowering and supportive to a person with a disability. The BCI will capture the motor imagery. The BCI will classify the motor imagery with an ADS classifier. The robotic prosthetic hand may be enhanced with multiple sensors such as LiDAR, optical and infrared cameras. The ADS classifier is trained with processed training data from the EEG. Class 1, red circles. Class 2, blue crosses. The ADS classifier surface is biased using the Gaussian structure centered on the average of Class 1 and Class 2, an inverted Gaussian structure. A spatial filter was used to reduce the unnecessary spatial EEG electrical activity and highlight a particular location of interest. In addition, the spatial filter will maximize the signal-to-noise ratio, such that accuracy of EEG-based communication will be improved. The surface of the ADS classifier will change when the training data is applied. Each training point will have a corresponding Gaussian structure. A Class 1 training point will be a positive Gaussian structure. A Class 2 training point will have a negative inverted Gaussian structure. The ADS model surface is constructed by combining the likelihood bias and the training data. You can observe how the surface of the ADS classifier changes as the training data is applied. The diagram shows a close-up of the ADS classifier surface. The peaks are the Class 1. The troughs, or the inverted peaks, are the Class 2. It could be possible to use artificial intelligence to maybe unlearn bad data, or you could fix and repair the surface of the ADS classifier. Here is a side perspective view of the Adaptive Decision Surface ADS classifier. This ADS is trained with the motor imagery training data. The vertical black line shows the test data. The ADS classifier has not seen this data before. The classification on the vertical lines is determined by where the vertical lines interact with the three-dimensional adaptive decision surface. Generally, if the test data is above the ADS surface, then class the test data point as Class 1. Example, Class 1 command to open the robotic prosthetic hand. If the test data is below the ADS surface, then class the test data point as Class 2. Example, Class 2 command to close the robotic prosthetic hand. The preliminary results shows comparable performance of the non-adaptive decision surface classifier with other classifiers. However, the adaptive decision surface classifier showed an increase in performance. Using multiple sensors on the robotic prosthetic hand will reduce the workload for the user. A range of sensors could be image processing. If the system is able to recognize objects such as a knife, a fork, spoon or drinking cup, the robotic prosthetic hand will be able to configure the hand for action associated with using a knife, fork, spoon, or handling a drinking cup. Audio processing, listening to when the cup makes contact with the table following the cup placement by the robotic prosthetic hand. Proximity LiDAR sensor detects the distance of the object. Pressure sensors signal how tight the object is held. The following is a LiDAR demonstration of grasping an object with a robotic prosthetic hand. A brain-computer interface is not connected and not used by the robotic prosthetic hand. If the prosthetic hand recognizes a drinking cup and detects the temperature, then the system could handle the physical manipulation of using the cup safely and reduce the workload for the user. If the system was able to recognize a knife, a fork, or a spoon, these utilities are different and are used differently. The robotic prosthetic hand should operate in a manner to suit the identified objects. Image processing patents. In 1994, my object recognition software was successfully developed and patented in 1996 and 2006. The boundary shape of the object is captured and the center of gravity of the shape is ascertained. If this initial capture is to be later used to be recognized by the system, then the boundary data points are programmed into the memory matrix. Each corresponding data point is surrounded by a square patch or cell of predefined data value. Later, when the system is used to identify an object and its orientation, the boundary data is extracted from the sampled image. The center of gravity of the boundary data is used to rotate the boundary data over the memory matrix center of gravity. The template data patch or cells in the memory matrix will fire when the boundary data points correspond with the patch or cells. The accumulation of firing patches or cells will indicate the certainty of the object identification in the memory matrix. This video shows the object recognition process in action. On the right of the screen, the boundary data points of the object is rotated around the center of gravity. On the left of the screen, the memory matrix data cells will fire when the boundary data points are within the data cells in the memory matrix. The memory matrix will update only when there is a greater number of orientation data cells firing. This concludes the presentation. Thanks for watching.